All right, so here's a quick guide to the solutions to the interference and standing waves quiz. Number one, we have 2 points that are half a wavelength apart. So if this is the first graph where x is shown, we expect then y would be half a wavelength. If this is at a crest, this is at a trough. When x is at a trough, y would be at a crest. So in other words, we want a waveform that looks like this, and that's going to be A. Okay, we have two waves that are meeting. They're going to overlap, so that's going to be constructive interference. So basically I have the rectangle here, and then I'm just going to superimpose on top of that the triangle. Okay, and so which one matches that? That's going to be B. 3 is destructive interference. Destructive interference occurs when we are, or maximum occurs when we are half a wavelength apart. So you want to look at those fractions. So this is lambda over 8, this is lambda over 3. Lambda over 3 is closer to a half a wavelength, so we're getting greater and greater in destructive interference. If they're asking about constructive, constructive occurs greatest when we're closer to 0 or 1. So this is closer to 0, so it's high constructive, low constructive. All right, before we didn't talk about much, so I'm just going to make this a non-factor for the quiz. If you want continuous interference, you have to have a constant phase difference. You have to have two waves that are either start out in phase, out of phase, but they remain in phase or out of phase the entire time. They can't be shifting their phases. All right, standing wave, successive nodes. Okay, so let's say we do a fixed string. So let's say there are nodes for fixed string. Here's an anti-node, node, node. And then a half a cycle later, it looks like this. But regardless, if I'm between the nodes, every point on the wave is at a different amplitude. Frequency isn't going to be different because that depends on the source, and the source isn't reflected in the shape of the standing wave so much. All right, now getting to a little bit more difficult problem. All right, number 6. If you know how to look at this right, it's pretty straightforward. We have our two sources right here, and so we want to look at path difference. So the path difference of 0 is the bisector between them, and that's this zone here. So the path difference is 0 wavelengths, and that's constructive interference. If I want the next zone of constructive interference, I want to go to our path difference of 1 wavelength, which means if I go right here, that's a 1 wavelength path difference, or I could say it's right here is 1 wavelength on either side, because the wave from here to here had to travel further than this one, and since we see the crests here, they are, if you will, amplified, we know it's constructive interference. So it's 1 wavelength, then this is a 2 wavelength constructive interference, 2 wavelengths over here. We're looking for 1.5 wavelengths, so it would follow if this is 0, a half would have nothing, destructive interference, 1, 1.5 destructive, and so that's our answer. Number 7, we have a pulse hitting a medium, a boundary, and bouncing off. And the key thing about that, because that's important for resonance or standing waves, is that it inverts. So if it inverts, we know it's going to be either A or C. So how do you distinguish between two is look at the leading edge. The leading edge of this one is the long slanted one, so that has to remain the leading edge when we come out. So I'm going to draw it like this, and then I'll explain why. Oops, stop correcting me. Okay, so notice in my poor drawing here, this is the leading edge, and this is the more steep edge, which should be reflected there. This is in front because the wave is now moving that way, and this is behind, so this is choice A. Number 8 requires a thorough explanation. I've put 4 points there that you need to highlight in order to get full credit. If I could just scroll down, that would be nice. This thing don't let me. Right, so you want to, so 4 things you want to say is you want to mention something about the frequency of the voice. You can call that the driving frequency. That has to match the natural frequency of the crystal. So that's 2 statements you need to make, and you can make it in 1 sentence. So when you have the net driving frequency matches the natural frequency, then you need to use a term somewhere, resonance or constructive interference, doesn't matter which one. And then to bring it home, constructive interference or resonance gives you an amplification, and that amplification leads to the breaking of the glass. Okay, so that's a 3-point problem. All right, next problem is more mathematical. You had to read it carefully. So we're standing somewhere between two speakers. It does not say halfway between. It just says directly between. We're not off to the side. Okay, so we want destructive interference. Destructive interference means we are a half a wavelength difference or 1.5, etc. So this is how we break it down. You're told that we're 0.8 away from one of the speakers. So you should show some work that that's 0.64 wavelengths. In other words, I just take this number and divide it by the wavelength of one wave. That's where I get this. So if I know I want destructive interference, then I want the path difference to be either a half a wavelength, 1.5, 2.5. I'm just keep it simple. Let's make it a half. So if this distance from here to here is 0.64, then, and I want the difference to be a half, then this distance could either be 0.14 wavelengths, right? If I just subtract a half a wavelength, or it could be 1.14. You choose. It doesn't matter. There's multiple answers here. So if I know that this has to be a half, 0.14 wavelengths, because again, this distance minus this distance would give me a half, then I could translate 0.14 wavelengths into an actual distance. In other words, I just do the reverse of this. I multiply this by 1.25, and I get this number, and then I take that distance, add it to the original distance, and I get 0.975. If you went with the path difference, or with this path length to be 1.14 wavelengths, then this distance would turn out to be, let me look it up. As many people did that way, that would turn out to be 1.425, and if you add it to the 0.8, you get 2.225. Okay, the superposition. So first of all, the maximum amplitude is going to be when it's at a peak, which is right here. Excuse me, when they overlap at the greatest amount, and that would give you 1.4 millimeters. And then I just drew this in beforehand, but basically you just go along, you know, maybe every line or every other line and just add up the respective amplitudes. When I did that, I get mine poorly drawn, but I get peaks at 1.4, 1.4, and then negative 1.4 here. And just look at the spacing to make sure that's correct. Okay, last set of problems with standing waves. All right, how many nodes and antinodes? There's 1, 2, 3, 4 nodes where we have no amplitude, and between our antinodes there are 3, not 6. 1, 2, 3. Okay, so if we know the total distance is 0.6 meters, what is the wavelength? Well, you could do this in a few ways. You could show, well, here's one wavelength, and that's right there, 0.4 meters. Or you could say within this full length is 1.5 waves. So the wavelength would just be the length, 0.6 divided by 1.5. Either way, it gives you 0.4. So if the frequency is 800 hertz, what is the frequency of the fundamental? Okay, so this is a higher harmonic, and the fundamental is the simplest one. So based on what we know about fixed string, this is the third harmonic. Now you can do this more mathematically. I'm just going to do the shortcut. Okay, so third harmonic because it has 4 nodes, whereas the fundamental only has 2 nodes. So if that's the third harmonic, what that means it's 3 times the frequency of the fundamental. So the fundamental would be 1/3 that, 1/840 divided by 3, which is 280 hertz. Okay, last one, open and closed pipes. We want to know the ratio of frequencies of an open versus closed. So open pipe, you have to have antinodes at the ends and therefore 1 node between. Okay, and the key point is within net L is a half a wavelength. Whereas in a closed pipe, this must be a node. This has to be an antinode. So I get that sideways, like champagne glass. The key thing is that's 1/4 of a wavelength. Okay, now we want the ratio of their frequency. So I want to translate to the frequency. So how do I do that? Well, we know that frequency is V over lambda. So this is going to be equal to V over half a lambda. I'm sorry, I forgot to do this. Lambda is 2L. If I solve for that, so that's 2L here. By the same reasoning, the frequency of the closed pipe is V, same velocity because they're the same medium, over 4L. Because if I solve for lambda here, I get 4L. Whoops. So now I want to do the ratio. So F open to F closed is going to be V over 2L over V over 4L. V's canceled, L's canceled. 1/2 divided by a quarter is 2. So the ratio is 2 to 1 for open to closed.